For section 7.3, we're going to look at the other identities that we have on our identity sheet, starting off with the double angle identities. I want to show you first where these come from. They actually come directly from the addition and subtraction identities. So if for my sine x plus y, if I actually call that x plus x, let's just do the plus, not the minus. So sine of x plus x is sine of 2x, which is double angle. Well, I'd have sine x cosine x plus, if I read this backwards, sine x cosine x. That's 2 sine x cosine x. They're like terms. So again, the double angle is just kind of an application of the addition identity for sine. Similarly for cosine, if I, instead of calling it y, call it x as well, cosine of x plus x would be cosine of 2x. Remember, cosine flips the sign, so this would become the negative. I'd have cosine x times cosine x, that's cosine squared. Then I'd have sine x times sine x, that's sine squared. So I end up with cosine squared minus sine squared. Now, there are two other cosine identities on here. 1 minus 2 sine squared and 2 cosine squared minus 1. You can use any one of the three when you're doing a cosine double angle. They're all the same. I just want to quickly show you where they come from. If I take this first one, I'll call that the parent one, and I use the Pythagorean identity to replace cosine squared with 1 minus sine squared, and I still have minus sine squared. So I substituted for cosine squared with 1 minus sine squared. Well, this would be 1 minus sine squared minus sine squared. That's 1 minus 2 sine squareds. So that's just another version. So that's combining the double angle for cosine with a Pythagorean identity. You could get the third one just by replacing sine squared with 1 minus cosine squared. Those other two versions of the cosine double angle will lead us to the lowering power identities, which we'll get to in a little bit. So, I'm doing this on a different program, by the way, in case you're wondering why it looks different, just because Word is being a little strange right now on mine. So, I do have another verse to Jingle Bells for this, and this is on that trig identity Jingle Bell PowerPoint. So 2 double the angle, 2 sin cos is sine, 2 sin cos is sine. It was 2 times sine times cosine. For cosine, just use this one, both squared of cos less sine. Both squared of cos less sine, because that would be both squared. Less in math means minus, cos less sine. So 2 double the angle, 2 sin cos is sine. For cosine, just use this one, both squared of cos less sine. Took me a long time to get that to actually work. May not be the best, but it's the best I can do. And remember, we had the other one for the addition and subtraction. As I mentioned, if it's tangent, oops, that's not what I wanted. If we're doing tangent, I will give you that one, so you do not have to have that one memorized. But sine and cosine, you need to have their addition, subtraction, and their double angle. And for cosine, you only really need the first one. Again, I'll be using the other ones, but right now you only need the first one. Okay, so let's actually try to do some problems with this. I want to find the double angles for sine, cosine, and tangent. I'm given what sine x is, but I want to know what sine 2x is. Now, what students will think is, oh, I just take the sine and I double it. Not at all. Not even close. That's not the identity. I need to draw myself a triangle in the correct quadrant. Well, sine is positive, but secant is less than 0. That means secant is negative, which also would mean that cosine is negative. So the quadrant where sine is positive, but cosine is negative would be in the second quadrant. Now, this is one of those functions where it's not one of my 30, 60, or 45. So I'm going to say, okay, sine from my reference angle would be opposite over hypotenuse. By Pythagorean theorem, I can figure out the adjacent to be 12. So now I can apply the identities. So 2 double the angle 2 sin cos is sine. So this would be 2 times the sine, which is 5 over 13. We were given that. Times the cosine from my angle. The cosine would be adjacent 12 over hypotenuse, which is 13. But remember, we're in quadrant 2, cosine's negative there. And so now I just multiply these together. Be careful. Sometimes I see students multiply the top and bottom by 2. That's not what multiplying by 2 is. Think of it like 2 over 1, if that helps. So just multiply across the top. 2 times 5 times negative 12. That's going to give me negative 120. 13 times 13 is 169. And there's the sine. For the cosine, 2 double the angle, 2 sin cos is sine. For cosine, just use this one, both squared of cos less sine. So the cosine of x was negative 12/13. And I'll square that. Minus the sine of x was 5/13. That's going to give me 144 over 169 minus 25 over 169, which will equal 119 over 169. So there's the cosine of 2x. Again, I'm not just doubling the trig function on any of this stuff. It's double whatever the original angle was, which changes your triangle completely. For the tangent, again, you do not have to memorize tangents, double angle identity. It's 2 times the tangent. Well, the tangent would be negative. The tangent from my reference angle on my triangle is opposite over adjacent, 5/12 over 1 minus the tangent squared. So 1 minus negative 5/12 squared. You'll end up with negative 5/6 on top. On the bottom, you'd have to get common denominators. Be careful when you square, that's going to be positive, but you're still subtracting it from 1. You'll end up with, on the bottom, let's see, 119 over 144. And again, that's getting common denominators and all that stuff. If I then multiply by the reciprocal, this would turn into negative 5/6 times 144 over 119. If you reduce the 6 and the 144 and then multiply, you'll end up with negative 120 over 119. Now, I want to show you that is using tangent's double angle identity to get that. On this particular problem, though, I didn't really even have to do all that green stuff. I knew what the sine was. I knew what the cosine was for 2x. Remember, tangent is just sine over cosine. So if I would have just taken that divided by that, meaning multiplied by the reciprocal, the 169s would cancel, and you would have gotten that anyway. So I didn't really even need to do it. For number 2, we want just the sine this time. Sine of 2 theta. So again, that does not mean take the sine and multiply it by 2. It's saying if I doubled this angle, what would it be? So I have to use the identity. So let's try that again. To double the angle, 2 sin cos is sine. Okay, so I was already given the sine. It's -1/7. I need to figure out the cosine still. That's where I have to build a triangle again. This one just flat out tells me what quadrant I'm in. I'm in quadrant 3. The sine would be opposite over hypotenuse, again, from my reference angle. So if I do a little Pythagorean theorem, you'll get root 48 for your missing side, which can turn into, you do a little factor tree on it, simplifying it, it's 4 root 3. So that was just using Pythagorean theorem. So my cosine would be adjacent, 4 root 3 over hypotenuse, 7. But cosine's also negative in that quadrant. So I have a negative times a negative, so my answer is going to end up being positive. If I multiply 2 times 4 root 3, that's going to give me 8 root 3. 7 times 7, 49. And there's my answer. For number 3, these are ones where we're trying to condense it down as much as possible. So basically, these are working the identities, but in reverse. So I'm going basically from the right side to the left side. So 2 sin cos, that is what it looks like when I expand out the sine double angle identity. So my angle x for this would be 41, really. That's the x angle according to the identity. So this would be sine 2 times 41. This would be the sine of 82 degrees. I don't know what that is, so we're good. For letter B, both squared of cos less sine. That is the expanded out version of cosine's double angle. And again, the 17 degrees would be my x angle, so it's 2 times 17 degrees, which will give me the cosine of 34. For letter C, again, it's both squared of cos less sine. So again, that's cosine's double angle. Now you got to be careful here. So cosine of 2 times some angle. The x angle this time is 5 theta, which is fine, just has a variable in it. So I just multiply those together and get 10 theta. So all I was doing was condensing down. I was trying to recognize the expanded out version and condense it down to its simpler version. So the next group of identities we're going to look at are the lowering power identities. You can see that they drop the power down by 1, squared to not squared, squared to not squared, so on and so forth. We're not going to be using these in this class. You'll be using them sometimes in calculus. But I want you to see where they come from. They actually come from cosine's double angle variations. So if I take this variation, that cosine 2x equals 1 minus 2 sine squared x, I'm going to solve this for sine squared. So I'd subtract 1. So I'd have cosine 2x minus 1, oops, inside there, minus 1 equals negative 2 sine squared. And if I divide by negative 2, I can basically switch the signs in the numerator around. So the negative 1 becomes a positive 1. The positive cosine 2x becomes minus cosine 2x over 2. So again, I basically just took that negative and divided it into both of those. But when I divide over the negative 2, I'm left with sine squared. So sine squared is 1 minus cosine 2x all over 2. So that's where this lowering power comes from. It actually comes from the double angle. So you can see we got the double angles from the addition subtraction. We get the lowering powers from the double angles. There's a logic to this. If I took the other cosine double angle variation, and I solved for cosine squared, I'd add 1 over. I would divide by 2. And I get that cosine squared is 1 plus cosine 2x over 2. The lowering powers you will not need to memorize at all. We are not going to use them. And you can see that if I did sine squared divided by cosine squared, so if I took that divided by that, I would multiply by the reciprocal, and you would get the tangent squared lowering power identity. Again, we don't need to know these ones, but the reason I show them to you is because they lead to the half angle. So the addition subtraction identities led to the double angle. The double angles lead to the lowering powers. The lowering powers are going to lead to the half angles. And it's actually a very quick little bit of algebra that gets me there. I'm going to take the lowering power, sine squared one, and I'm going to substitute in for x with x over 2. So if this was x over 2 instead, that would make this over here x over 2. Well, 2x over 2 is just x. So that became 1 minus cosine of x over 2. And now if I square root both sides, the square would go away on sine. That's gone. And I'm left with sine of x over 2 is the square root of 1 minus cosine x all over 2. And there's a plus or minus out there. We'll deal with that plus or minus when we get into the problems. So from the lowering powers, and all I do is replace x with x over 2, and then I square root both sides, those lead to the half angles. So they're built off of one another. So it's good to see the connections because it helps you if you forget them. Now for the half angle, just like with the other ones, I will expect you to know sine and cosine. I don't have any song for those. Those ones you just got to memorize, but you can see they're almost identical. Sine, it's a subtraction. Cosine, it's an addition. Tangent, again, I will give to you if it comes up.